Welcome back to our OEIS deep dive. Today we're going to be tackling A000087,
Okay.
which is a sequence that
Yeah.
combines graph theory and topology.
Uh-huh.
It has to do with counting unrooted, non-separable planar maps with binna edges
Right.
and a distinguished face.
Okay.
So,
Sounds pretty complicated, mate. We can
yeah.
break it down a little.
Okay, so first of all,
Mm-hmm.
what is a planar map?
A planar map, you can think of it like
Yeah.
drawing a network on a flat surface.
Okay.
And so it's divided up into different regions using points, which we call vertices.
Yeah.
We use lines connecting those points, which we call edges.
Okay.
And then the spaces enclosed by those lines we call faces.
Okay, so like if you had a map of like the subway lines,
Mm-hmm.
the stations would be the vertices,
Right.
the tracks would be the edges,
Exactly.
and the neighborhoods they enclose would be the faces.
Yeah, exactly like that.
Okay,
Yeah.
gotcha. And then, so non-separable, what does that mean?
Non-separable just means that you can't cut the map into two separate pieces
Oh,
by snipping just one edge.
okay.
So it's like,
So it has to be well connected?
yeah, think of it like a network with no single point of failure.
Okay,
Um,
gotcha.
yeah.
And then what's this distinguished face?
Distinguished face is just one specific face that we choose to highlight.
Oh,
So you could think about it as picking out a particular neighborhood
Okay.
on your map.
so we're counting these well-connected networks on a flat surface
Right.
with a highlighted region.
Yeah.
Why are we counting this? What's so special about this?
Well, these maps actually have surprising applications in different fields.
Uh-huh.
For instance, in computer science.
Okay.
Understanding network connectivity is super crucial.
Okay.
And these maps provide a model for analyzing just that.
Okay.
So imagine you're designing like a robust communication network.
Yeah.
These maps can help you understand its vulnerabilities and optimize its structure.
Yeah, that makes sense.
Uh,
Like, I could see how that would be useful outside of
yeah.
just pure math theory.
It actually goes even further than that.
Okay.
These maps are also used in physics to model 2D quantum gravity.
Wow.
And they also pop up in the study of permutation patterns,
Okay.
which are basically just specific arrangements of numbers. It might seem totally unrelated,
Yeah.
but it just shows the interconnectedness of different mathematical concepts.
So this is like a pretty fundamental structure that we're looking at.
Yeah, precisely.
With connections to a lot of different areas.
And recent research has uncovered this fascinating connection between these maps and a special kind of tree.
Trees.
Yeah.
Like with branches and leaves.
Well, not quite those kind of trees,
On the
but the
side.
concept is similar. So
Yeah.
these are called beta-1 trees, and they have specific rules
Okay.
about their structure and labeling. And it turns out there's this one-to-one correspondence between these trees and the non-separable planar maps that we're discussing.
So like for every
Yeah.
map,
Yeah.
there's a unique tree that represents it.
Exactly.
Vice versa.
Exactly. So
Okay.
this connection lets us study the maps through the lens of trees,
Okay.
which can be a little bit easier to analyze in some ways.
Okay.
It's kind of like having a new set of tools to understand these complex structures.
So how does that connection actually work? Like, can you give me an example?
Absolutely. So let's
Okay.
talk about two faces.
Okay.
These are regions in the map that are bounded by only two edges.
Okay.
So like think of it like a narrow alleyway on your map.
Gotcha.
It turns out that the number of these two faces in a map
Yeah.
can be determined simply by looking at the labels of certain nodes in the corresponding beta-1 tree.
Wow. So you can actually analyze the tree
Yeah.
and learn something about the map's structure.
Exactly.
That's really powerful.
Yeah, and it gets even more intriguing when we delve into specific types of maps, like primitive maps.
Primitive maps, what are those?
So those are a special subset of non-separable planar maps where almost all the faces, except for one specific one, are not two faces.
Okay.
So think of them like the simplest building blocks
Okay.
for constructing more complex maps.
Of like the atoms
Yeah, exactly like.
of non-separable planar maps.
Uh-huh.
Gotcha.
So how do they fit into the picture with the trees?
Yeah.
Well, it turns out that these primitive maps correspond to a very specific type of beta-1 tree.
Okay.
And this connection allows us to count them and understand their unique properties much more easily.
So it's like we're zooming in on a specific part of the map.
Yeah,
And the corresponding tree structure reflects that focus.
exactly.
Right.
And the research doesn't stop there.
Oh.
They've even delved into multiple edge-free maps.
Okay, so no redundant connections between 2 points.
Yes,
Yeah.
exactly. And you wouldn't believe this, The beta-1 trees that correspond to these maps have a unique characteristic. Every internal node, which is basically a node that's not a leaf,
Okay.
in the tree must have a sibling.
So there's a very specific branching pattern in the tree that reflects that property of the map.
Exactly.
Like the tree is encoding this information about the map's structure.
Exactly.
Wow.
And this discovery opens up a whole new way to explore and analyze these multiple edge-free maps.
This is really cool. And all this from this seemingly simple sequence of numbers, A00000087.
Right.
Who would have thought it would lead to all this complexity in these connections across different areas of math?
Yeah, that's the beauty of the OEIS. It's full of surprises, and there's still more to uncover.
Oh, there's more.
Yeah, we haven't even touched on the connection to permutations yet.
Oh, yeah, you said that earlier.
Yeah.
How do permutations fit into all of this?
Well, it turns out that these non-separable planar maps can also be represented as special types of permutations called non-separable permutations. And these permutations have to avoid certain patterns.
Okay.
And that's key to the connection with the maps.
So we've got maps, we got trees.
Yeah.
And now we got permutations all linked together.
A web of interconnected mathematical concepts.
Wow, this is amazing.
And this web is even more intricate than you might think.
Oh.
We'll unravel it further in the next part of our deep dive.
Well, you've definitely piqued my interest.
Okay, great.
I can't wait to hear more about this fascinating connection between maps, trees, and permutations.
All right.
This is really cool.
Stay tuned. We're just getting started.
Okay. Okay, so before we get into permutations, you mentioned that these special non-separable permutations have to avoid certain patterns. What do you mean by that?
It all has to do with how these permutations are actually constructed.
Okay.
And you remember how we talked about decomposable and indecomposable beta-1 trees?
Yeah.
Well, it turns out that we can actually mirror those construction steps with permutations.
Okay.
And that's what gives us this really fascinating connection.
So we're essentially building permutations in a way that mimics the structure of these special trees.
Exactly.
Okay.
So with decomposable trees, you're basically gluing smaller indecomposable trees together at their roots to create a bigger tree.
And how does that translate into the world of permutations?
So you take several indecomposable permutations and arrange them side by side.
Okay.
And you adjust the numbers in each subsequent permutation to maintain an overall increasing order.
Okay.
So it's kind of like...
So like building a bigger sequence from smaller, kind of like self-contained sequences.
Exactly. So the way we construct both decomposable trees and permutations reflects this idea of combining these smaller units. Now, for indecomposable trees, things get a little bit more intricate. You extend a tree by adding an edge to a node that has a label that's less than or equal to its parent's label. It's a specific rule that governs how these trees can grow.
And how do we mirror that process in the world of permutations?
So imagine you have an existing permutation. To make it bigger, you would insert the largest number, let's just call it n, right before one of its left-to-right maxima.
What's a left-to-right maxima?
These are like the peaks in the permutation where there's no larger number to the left.
Okay, so we're strategically placing this largest number based on the existing peaks in the permutation.
Exactly. But there's a catch. You have to kind of rearrange the pieces of the permutation in a very specific way to ensure that the resulting permutation is still indecomposable and avoids those forbidden patterns we talked about earlier.
So it's not just like sticking the largest number wherever you want.
Right.
There are rules to make sure.
Yeah, it has to be well-behaved.
Yeah, well-behaved.
In a sense.
Okay.
And by following these rules, we create this direct link between the construction of beta-1 trees and the construction of these special permutations.
So it's like we're translating the language of trees into the language of permutations.
Exactly.
And because we already know that the trees correspond to the maps, we've essentially created a bridge between maps and permutations.
Exactly. This connection, mathematicians like to call it a bijection, is incredibly powerful. Because it allows us to translate properties, the trees, into properties of the permutations and vice versa.
Can you give me an example of how that works in practice?
Absolutely.
Okay.
So remember those two faces that we were talking about?
Yeah, those are the regions in the map that are bounded by two edges.
Exactly. And we said that we could actually count those by looking at specific labels in the beta-1 tree.
Right.
Well, this property actually translates directly into what are called mesh patterns in the corresponding permutation.
What are mesh patterns?
So mesh patterns are a way to describe patterns in permutations that take into account not only the relative order of the elements, but also their positions within the permutation.
So it's not just about...
It's a little bit more detailed than just looking at the order of the elements.
So it's not just about what numbers come before and after each other.
Right.
It's also about where they are.
It's also about their location.
In the sequence.
Exactly. And in the case of two faces, the mesh patterns actually involve the largest element engro and how it's positioned relative to the other elements in the permutation. So by analyzing these patterns, we can actually identify which permutations correspond to maps with those internal two faces.
So we're basically using these mesh patterns as a sort of fingerprint to identify specific structural properties of both the maps and the permutations.
Exactly. And it gets even more powerful.
Oh.
Researchers have actually identified specific mesh patterns that must be avoided if a permutation is to correspond to a primitive map.
Okay, so those primitive maps being...
Remember, those are those fundamental building blocks.
Yeah, like the atoms.
Exactly.
Right.
So by looking for these specific patterns, or rather the absence of these patterns, we can actually pinpoint the permutations that correspond to those special primitive maps.
So we're refining our understanding of
the
permutations based on the properties of the maps they represent.
Yeah, it's kind of like using a sieve to separate out different types of permutations based on their kind of hidden connections to the map structure.
So by studying these permutations, we're gaining a deeper understanding of non-separable planar maps and their properties.
Exactly. This connection between maps, trees, and permutations is incredibly rich. And it's opened up this whole new avenue of research in this area.
I'm really starting to see how powerful this idea of mapping between different mathematical structures can be.
It is.
It's like we're translating knowledge from one domain to another,
exactly,
revealing hidden connections and insights.
It is, and the more we explore, the more connections we find. In fact, there's another really fascinating aspect to this that we haven't even touched on yet.
Oh, do tell.
You remember those multiple edge-free maps?
Yes, the ones with no redundant connections.
Exactly. Where no 2 points are connected by more than one edge.
Right.
Their connection to permutations has some particularly interesting features.
Okay, so back to those maps with no redundant connections. What's so special about their relationship to permutations?
Well, let's dive into that in more detail.
All right, so let's talk about these multiple edge-free maps and their connection to permutations.
Okay.
What's so special about them?
Well, remember how these maps are kind of a subset of two-face free maps? That's like the key starting point. So those same forbidden subtrees that define the two-face free beta-1 trees also apply here. But there's kind of an extra layer of structure.
Okay, so those forbidden subtrees are like a set of rules that prevent certain tree shapes from occurring.
Exactly.
If we want to represent these maps.
And what's really remarkable is that researchers have discovered this unique characteristic of beta-1 trees that corresponds specifically to multiple edge-free maps. Every internal node, so those are the nodes that have children, must have a sibling.
So there's a kind of paired branching going on. Like every time a branch splits, it always splits into at least two new branches.
Precisely. So this kind of enforced branching pattern reflects the multiple edge-free property of the map. And it's just like a beautiful example of how this structural constraint in one mathematical object, the map, manifests as a specific pattern. In another, the tree.
So this sibling rule for the trees gives us a really powerful tool.
It does.
For analyzing these maps. How so?
Well, it allows us to derive these lower bounds on their number. So like counting these maps directly is pretty tricky, but by studying the corresponding trees, we can get some pretty clever estimations.
Can you walk me through how that works?
Absolutely. So let's just start with a simple scenario. Imagine all the labels in our beta-1 tree, except for the root, are restricted to just being 1.
It's a very specific, simplified kind of tree. Okay, what's the advantage of doing that?
Well, since every internal node has to have a sibling,
Right.
we can basically ignore the labels
Okay.
for a moment and just focus on the tree structure.
Okay.
So it becomes like a pure counting problem of how many ways we can arrange these branches with the sibling rule in place.
So we're stripping away some of the complexity to make
Exactly. And it turns out this simplified scenario actually corresponds to a well-studied type of tree.
Okay.
It's called a rooted tree, where every node has a sibling. And we already have these mathematical tools called generating functions to count these types of trees.
So we can piggyback on our existing knowledge about these simpler trees to estimate the number of our more complex ones.
Precisely.
And then in turn the maps.
And that gives us this lower bound.
Okay.
So we know there are at least this many multiple edge-free maps.
Okay.
Because we've counted a subset of their corresponding trees.
That's clever.
Yeah.
But it's just a lower bound. Can we get any more accurate?
So the trick is to kind of gradually increase the complexity of our beta-1 trees by allowing for labels greater than 1.
Okay.
So for example, we can derive a generating function for trees where labels are restricted to be at most 2.
Okay.
Still enforcing that sibling rule.
Okay.
And then we can move on to labels up to 3.
Okay.
And so on.
So it's like we're building a ladder of increasingly accurate
grave edges.
estimations or approximations, getting closer and closer to the true count.
And this method has actually yielded remarkably accurate estimations for the number of these multiple edge-free maps.
Wow.
Even though like the exact enumeration is still like an open problem in mathematics.
This has been an amazing journey.
Yeah, it has.
We started with this seemingly simple sequence, A000087.
Right.
And it took us through maps, trees, permutations. And now even these like really clever counting techniques.
It's really amazing.
It's amazing how it's all interconnected.
It really is. It's a testament to the power of mathematical abstraction and just the beauty of finding these hidden relationships between these seemingly like disparate concepts. The OEIS is full of these treasures.
Absolutely. And you've definitely inspired me to keep digging deeper into the OEIS and see what other mathematical wonders I can uncover.
There you go.
Well, thank you so much for guiding me through this fascinating deep dive.
My pleasure. Keep that curiosity alive, and who knows what you'll find.
Absolutely. All right. Thanks again.
All right. See you next time.